Good morning, students.
Good morning, sir.
Can you all see this? Can you guys see the screen?
Yes, sir.
Yes, sir.
Okay, the last time the video was not complete, so I'm just going to go over again. So we calculated V1. Remember, we calculated this using the voltage divider from the circuit. So we were able to find V1T, this amplitude. So therefore, the power is V1 squared over Z0. And this is the amplitude. Therefore, it's going to give you 1/4 V0 squared over Z0. So this is the power produced at the input right here, the power produced right here. So this power wave or voltage wave, so this voltage wave travels to the load through the transmission line that has a length of lambda over 4. Since this is a lossless line, assuming lossless, therefore, power is directly delivered to the load without any loss. The power at the load is given by V2 squared, the voltage across the load, divided by the load resistance. And that's going to be equals to the power at the input. The power at the input we calculated earlier, right here. Since this is lossless, power that is at the beginning of the transmission line is the same power at the end of the transmission line, because the transmission line is lossless. So we equate the power at the input and output, and then you solve for V2 squared. So solve for the voltage at the output. So when you solve it, you will end up getting a V0 over square root of 2. So that is the amplitude of the voltage, okay, when you solve it. But this voltage at the output will have a phase shift of minus 90 degrees, which is also same as minus j, which is also same as this. All these are the same thing. E to the minus j pi over 2. If you use the Euler, this is same as, so this is minus j. That's why it can be also represented with the exponential function, or it is also minus 90 degrees and is also minus j. It's minus j because the input voltage is traveling through a quarter wavelength. Quarter wavelength in degree is minus 90 degrees. So that is V2. Right here, it has a minus j. That's one way of writing. So if we want to convert this to time domain, it's going to be introducing a minus 90 degrees. The input doesn't have any phase shift. It was just cosine omega naught t. But now, with the effect of the wave traveling through the transmission line, created a phase shift. So therefore, at the output, the output is going to be sine omega naught t. The same amplitude, but it's sine. The input was cosine. See the relationship. Somebody is having the mic on. Please turn it off. So this is cosine. If cosine omega naught t if you copy paste, if you move it, it's here now. So if we move it by 90 degrees, it becomes sine. As amplitude. So that's all for, this was a continuation from the last time because the video was truncated at the last. So do you guys have any question? Any question? Hello?
No, sir.
No, sir.
Okay, now I'm going to do some examples related to the midterm. The midterm is, we already announced the date of the midterm, right? Let's do this. A transmitter is capable of producing 2 watt output power. So if you're confused, you can just draw the circuit diagram. Transmitter usually has some source impedance. It's a transmission line. And this is the load. Capable of producing 2 watts. That means that's available power. Available power 2 watts. Okay, let me write here, available power. The transmitter is connected to an antenna. So this is a load that is representing the antenna. A load representing an antenna. Having a characteristics impedance, therefore this is having a characteristics impedance of 75 ohms. 75 ohms. The transmitter is connected to an antenna having a characteristics impedance of 75 ohms. The connection is made using a lossless cable with a 75 ohms characteristics impedance. So it's good for you. 75 ohms characteristics impedance, 75 ohms at the load. Load also 75 ohms, and this one also is 75 ohms. So everything is well matched. The length of the transmission line is 11 lambda. Calculate the power delivered to the load. So what is the power delivered to the load? power P in is 2 watts. So what's going to P out? Okay guys, I give you guys a few minutes to think about this. For lossless case is P in is PL is 1/8 VG's amplitude squared over Z naught. This is the formula that we need to solve for this problem. So this reflection coefficient gammas of S is how much? Is equals to? Can anyone tell what is gammas of S? And what is gammas of L? The reflection at the load.
0.
75, sir.
Somebody said 0. Who was that?
Zach.
Zach. Yes, it's 0 because see, none of you are studying. None of you guys are respecting this class. There's only one person really bothered about these things. Because the source impedance is 75 ohms and the characteristics impedance of the transmission line is also 75 ohms. But they are the same. If they are the same, the reflection coefficient is going to be 0. Don't you remember how to calculate a reflection coefficient? So if you look very carefully, the characteristics impedance, if you look, this is also 75 ohms, right? And then
Yes.
the load impedance also 75 ohms. So they are the same. Therefore, the reflection coefficient at the load is 0.
Yes, sir.
So it's going to be 0 here because the reflection coefficient formula, you guys have to understand. So if you look at the formula here to find the reflection coefficient at the load is ZL minus Z naught divided by ZL. So if you guys missed the previous notes, please look at the video. Now if you look, these two are the same. 75, 75, 75 minus 75 is 0. As a matter of fact, you don't need any mathematics to know this because you know that the load impedance and the line impedance, they are the same. So the reflection at the load is 0. Do everybody see that? Is everyone able to follow this concept? Who cannot understand this concept? So therefore the power is Vg squared over Z naught 1 minus 0 over 1 minus 0. Because all the reflection coefficients are 0, 1 minus 0. So the power is simply 1/8 Vg squared. And that is equals to 2 watt, isn't it? It's the available power. Do you remember from the previous lectures? From the previous lecture, do you remember? That's available power. If there's no reflection, since there's no reflection, since P in the available power is also the power delivered to the load. So if you know the theory, you can answer this question in a couple of seconds. Correct, guys?
Correct, sir.
So the exam is going to be so easy. If you have been following the previous lectures, it will be easy.
No, sir.
Okay, next question, a signal generator with an internal impedance. Can you guys think about this question for a while? We have done something like this earlier, right? You have a signal generator. And it's delivering power, and that's a minus 1 dB attenuation, 1 dB attenuator. To a matched load. What does it mean by matched load? What does it mean by matched load? Jeff,
Yes, sir.
matched load means what?
50 loads, sir. 50 ohms.
50 load. Okay, 50 ohms, right? That means it's matched to the source.
Yes.
So good. So it is a matched load, 50. Find the resulting amplitude of the voltage at the load. So we want to find what is the amplitude. Amplitude. You can call this VRMS to differentiate that from instantaneous voltage. Because instantaneous voltage, usually the voltage is different at different time, right or not? Instantaneous. So we have this VRMS. That's what it means. So find out the VRMS. So in order to find the output voltage, we want the power at the output is VRMS squared over 50 ohms. So therefore you have to find what is VRMS. So in order to find VRMS, you can solve for VRMS. VRMS is 50 times P out a square root. So if you know a P out, you can find VRMS. P in is 2 dBm. After the attenuation, P out will be how much?
Let's say 1
1 watt. 1
dB.
unit? Huh?
1 dB.
1 dBm. We already went through, you look at the last one. The last video, I went through in detail. There's two ways of finding P out. One easier way, because they are log, you can just subtract them. 2 dBm minus 1 dB is 1 dBm. Now you have to convert this equation to find out your P out. You cannot put dBm here. You have to convert that to watts. So how do you convert that 1 dBm? P out is equals to 1 dBm. 1 dBm. Okay, convert that to milliwatts. Convert to milliwatts. Okay, all of you, please convert this to milliwatts.
The 1.2589 milliwatt.
Okay, 1.259.
89.
1.
2589, sir.
Okay, 2589.
Milliwatts.
From the previous video, you should know how to do this. Who don't know how to do this? Do everybody know how to convert? Definition of 1 dBm. Definition of 1 dBm, 10 log P out for 1 milliwatt. So right now, now then you solve for P out. Divide by 10 on both sides. You get 1 over 10 is log base 10 P out over 1 milliwatt. So that's going to be 10 to the power of 0.1 is P out for 1 milliwatt. Then therefore P out is going to be 10 to the power of 0.1 1 milliwatt. So that's going to give you 1.2589 milliwatts, or you can just simply say 1.259 milliwatts. And then from there, P out is Vrms squared over R, which is happened to be 50, is equals to 1.259 milliwatts. Right? We already have this formula earlier. We can simply use this formula. Vrms is 50 times 1.259. How much is that? How much is it?
0.25.
0.25 unit. Unit is what? 50, 1.259 10 to the power of minus 3. How much is that? Uh, 0.251 volt. B amplitude. When we talk about amplitude, we're talking about the maximum value. So this is amplitude. Or Vmax or Vamp is square root of 2 multiplied by 0.251. Any question?
No, sir.
Okay, midterm exam is on the 4th of 4 midterm. Proposed on the 4th of September 2020. Okay, this one you can see, you can briefly explain the skin effect in high frequency transmission lines. What effect has the skin effect on the high frequency signals? So this is the answer. The magnetic fields generated by the high frequency currents drive those currents to the outer edge of the conductor that carries them. So the higher the frequency, the thinner the layer of the metal available to carry the current, and the higher the effective resistance of the cable. The frequency dependent resistance gives rise to attenuation and distortion of high frequency signals. This is a cable. So all the charges, at low frequency, all the charges are uniformly distributed throughout the cross section when they flow, when the current flow. You know, at high frequency, what happens is the higher the frequency, at high frequency it moves to the surface. So now the same current, but in a smaller area to flow through, therefore it is going to increase the I squared R resistance. And the resistance will go up. Effective resistance to current flow goes up. And there's also a heating effect. Even at AC, already some current already flowing on the surface only. At RF, microwave is worse. So the higher the frequency, it will be much thinner. The surface, the cross-sectional area available for the current flow becomes thinner and thinner the higher the frequency, the more thinner it gets. Okay, this is an impedance. Impedance response. So this is the frequency on the vertical axis, on the horizontal axis. The vertical axis is the impedance amplitude of the impedance. The response, you can see the impedance is 100. Around here, it's 100 ohms. It's a resistive, purely resistive. And you can see it's around 100 ohms. And then after some time, this area, it's becoming capacitive. Because when the omega increases, 1 over omega becomes less, so it drops. So because this omega increases, as frequency increases, or as F increases, ZC decreases. So therefore it drops. After some time, it becomes inductive. This is the resonant point. At this point, you can see that it is purely real. The resistance, because the resonance, it has some resistance value, a small resistance, maybe around 1 ohms, maybe 2 ohms. After the resonance, it becoming inductive because ZL is j omega L. As omega increases, ZL also increase. So after a certain point, it becomes inductive. At this point, right there, ZC is ZL. Inductive capacitance and inductive reactances cancel each other. At that point, Z is purely real. So now I'm asking you to write an equation for this. You can start here. Start with the Z. The Z is R at lower frequency, so you can put R there. R, as the frequency increases, you have a capacitance Z, C, right? At lower frequency, so 1 over j omega C. Can I add like this? Is it possible to add like this? Because at lower frequency, Z is R, right? At lower frequency, Z is R. But then lower frequency means omega is like approximately 0. Let's say omega is 0, then this becomes 1 over 0. And therefore, this is R plus infinity. Therefore, the net impedance is infinity. But from this graph, you can see it's not infinity at lower frequency. It has a finite value of 100 ohms. So what should then how about you try this? So plus 1 over j omega c doesn't work. How about we put R parallel with capacitance? I mean, now we are looking at a circuit that is parallel Z. So in this case, j omega c parallel combination of this, R parallel with C, j omega CR. Sorry. R times 1 over j omega c divided by R plus j omega c. J omega c over R into j omega c over R. I'm just simplifying it by multiplying top and bottom by j omega c over R. That's going to give me 1 over j omega c plus 1 over R. Okay, this makes more sense because when omega is approximately 0, Z is R, right? As omega becomes larger, so therefore omega becomes larger, then omega j omega c is going to be getting very, very much bigger than 1 over R. Okay, just let me delete these things. Okay, omega is approximately 0. R is, Z is R. Okay, so Z is R. So as omega increases, omega increases this way, right? Either you can say F omega, it doesn't matter. As omega increases, the 1 j omega c, 1 over j omega c, sorry, j omega c. Looking at this equation here, we're just looking at this part. As omega increases, what happens is j omega c becomes much, much larger than 1 over r, correct? Therefore, in this case, you can simply ignore in this case, z becomes approximately 1 over j omega c. Therefore, this part of the circuit behaves as a capacitive impedance. Okay, this part of the circuit. So do you guys understand what's happening from year to year? From year to year, and then we already looked at from year to year. Now we look at this part here. Why is it going up suddenly? What can make it go up? So far we have come up with this equation: 1 over j omega c plus 1 over r. We have come up with that. So what will happen if I add j omega L? See, don't forget, this part here is R parallel with 1 over j omega c. Now we are adding j omega L. So as the frequency becomes much, much larger, see at this point right here, at this point, ZC is ZL. They cancel each other. Right? After that, what happens is the inductor takes over. As omega increases further, the inductive reactance becomes much, much bigger than the capacitive reactance. I'm not saying this. This curve is telling me that. At resonance, they cancel each other at resonance. At this point, you can clearly see the inductor is becoming much, much bigger than GC. So that can only happen if I add an inductor. Right here, we add the inductor. See, after some time, because we already, after some times, you know, the high frequency, 1 over, this is going to be as omega. What happens is as omega increases further, 1 over j omega c is going to be going to 0, right? So therefore, the inductive part is going to take over. So the second diagram for this is a resistor parallel with the capacitor and then in series with the inductor. This is impedance looking inside here. Any question? Any question?
No, sir.
No, sir.
Okay, here is another example. Maybe you can try to go through this by yourself. It's a purely mathematical. Impedance looking inside here. At what frequency, derive the frequency, the resonant frequency. You look inside here, Z is j omega L plus R over, sorry, plus find the resonant frequency. Okay, resonant frequency from the last time we know when will the resonant frequency happens. The resonant frequency happens when the inductive capacitance, sorry, when the inductive reactance is equals to the capacitive reactance. When they cancel each other, when the reactive part, that means the imaginary part, goes to 0, that's when you get the resonance. So therefore, you derive the input impedance and set the imaginary part to 0. And that will give you the resonant frequency. This is ZL, the j omega L is 1 over j omega C. Is j omega L is in series with the parallel combination of the capacitance and resistance. So that's going to be j omega L plus j omega RC divided by R plus j omega C. So that's a parallel combination of the resistance and the capacitance. Resistance and the capacitive impedance. Then from then on is going to be algebra. Okay, guys, try to do this. See, what do you get? You will get a real part and then plus imaginary part. Okay, you set the imaginary part equals to 0, and then you solve for omega. You separate the real and imaginary. So the real part inside here. How you do it? Please try. Please try on your own. That's all for today, guys. This is the answer. 1 over LC minus 1 over R squared L squared.
Multiply by the conjugate, right, sir?
Conjugate.
Yeah.
Yes, yes, yes. Who is this?
But Arvind, sir.
Yes. Yes, master. R minus j omega C multiply by conjugate top and bottom. The reason for multiplying by conjugate top and bottom, when you do that, this part here, the denominator becomes real. Okay? Okay, this is
Yes,
part
sir.
of assignment 1. Assignment 1 started now. Assignment 1 started. Assignment, right? So it's not assignment 1, it's assignment plus project. Assignment plus project. Assignment 1 and project is how many percent? 20%. So I'll see you guys next week.
Yes, sir.
Okay, sir.
Thank you, sir.
Yeah, thank you. Bye.
Use that.
Bye, sir.
Bye.